All right, folks, today we're going to be doing more with Trig models. We're going to look at some different applications from what we did last time, but we are going to use Desmos again. You should have received a code from me, otherwise you can find it on the agenda page with the 6 digits that you type in at student.desmos.com. Okay. I'll have you pause the video until you get logged into that because we will start with that today. Okay. What I want you to do is go through the first 3 screens, and as long as some other people have done this prior to you, you will see something on screen 3. You'll see all of the class's data. So you're given some information on the first screen, then you're asked to take your pulse and input some information on the second, and you'll see it pop up on the third. Okay, so take a couple minutes to do that, and then come back to the video so we can chat. Okay. Again, as long as someone has entered this, and I can just go to an example class that has already completed this. As long as someone's in here on the third screen, you're going to see some dots show up. And the purpose of this was for us to just get an idea of what a typical pulse is for folks y'all's age. And generally, you're going to see it range around the 70, but sometimes we see those higher rates, especially when we're not at rest, when you're doing physical activity, and lower rates at rest depending on the age. So what we're going to talk about today is an application with how this pulse that you take relates to your blood pressure. Now, I didn't ask you to take your blood pressure. It takes a little bit more equipment than that, but blood pressure is going to be our focus for today. So I want you to think about the definitions that you read on the first slide, thinking about the systolic and diastolic pressures, what they're measured in, and how that would relate to your pulse. Okay, and that's going to answer the question on the 4th slide. Okay, so think about that. Go ahead and enter what you think. You can hit that share with class button, and then come back to the video for more instructions. So hopefully you thought something a little bit about the specifically the blood pressure being related to your heart pumping the blood. Okay, so if you think about your heart pumping the blood, your heartbeat is when your heart is contracted, that muscle is contracted all the way. Okay, and then it relaxes, and then it contracts and relaxes and contracts, and it does that over and over again. Okay, and anytime we're repeating some cyclic idea between certain values, then that is going to be something that's periodic. And specifically for sine and cosine, when we talk about our parent functions, they're cycling between 2 set values. And those 2 set values, if we're modeling the blood pressure, are your systolic blood pressure and your diastolic blood pressure, your maximum and your minimum. And it relates to your pulse because our heartbeat is what's dictating when we get to our maximum, to our minimum, to our maximum, to our minimum as the heart contracts and expands. Okay, so what we're going to do is try to find an equation so that we can model this. And on your paper I gave you, I'm going to have you answer a little bit about this being periodic, but what we're going to do together is focus on one set example. So everybody in the room has a different heart rate or pulse, and they're also going to have different blood pressures. Okay? Each of us would have a different function to model our individual blood pressure with our heart rate versus another. So as we do this example, we're going to look at set values. So we're thinking about a healthy adult, a normal blood pressure that may sound kind of familiar to you if you've ever gotten your blood pressure taken at a checkup. 120/80 is kind of the range they're looking for adults at least. And so that 120 is talking about your systolic blood pressure and then your diastolic blood pressure for your 80. And then it gives us a heart rate of around 70 beats per minute. So what we're asked to do is use the cosine function so that we can measure blood pressure after X seconds after the maximum. What this tells us is we want to talk about the maximum in general. We're going to think about cosine as parent function. And on Desmos itself, it indicates even more specifically that we're going to assume that there's no H here. In general, when we are graphing something by hand here, unless we're given some extra context to indicate that we're starting so many seconds after the maximum or so many seconds after the average value, the midline, then we can start it wherever we want, and we want to do so in a way that makes our life easier. Okay, so we're going to have no h and actually start at the maximum, and using cosine will let us do that. Okay, so what I'm going to have you do here first to start with is we want to talk about those values, our 120, our 80, and the 70 that they gave us, and then talk about how that relates to some of these items in seconds, and you've got a bunch of space here to do any work that you need to. Okay? So we've already talked about the 120 and 80 relating to the blood pressures, but specifically those are our max values and our min values. And blood pressure was measured in millimeters of mercury. That was given on that first page of your Desmos. Okay, and then the other thing they gave us was dealing actually with the frequency. And we haven't talked about this word frequency in a while, so I want you to add here, it is the reciprocal of the period. Okay, and we can write reciprocal as 1 over that thing, or if we have a fraction already, just flip it. So when we talk about this 70 beats per minute, our instructions were given to us as change that to beats per second, change it to seconds instead. And that's because when we want to graph this, 70 beats per minute, if we only look at 1 minute, that'd be really fast and we wouldn't really be able to see a whole lot. So instead we're going to think about how many beats would show up in just a second instead. Okay, so that's going to be significantly less, and less means divide. We're going to take our 70 minutes and divide it by, or 70 beats, sorry, and divide it by 60 seconds to get 7/6. And that's talking about beats per second. Okay, so on here, our frequency, that's how often it happens, is 7/6 beats per second. And the reason I'm writing out the label like this is so we can really understand the period. Because remember, the period is the reciprocal of that thing. So all we have to do is take this and flip it over, and that includes the label. This really says 6/7 second. We don't even have a full second per beat. And hopefully that makes sense. If we think about this, if we are doing 70 beats per minute, and we know there's 60 seconds in a minute, we're going to have to be beating faster than a second. So that's what this says. We're beating, and it's faster than 1 second. It doesn't quite take 1 second to get there. Okay, so we've got our information here except for amplitude, and you'll notice that we also haven't talked about midline or K. Again, we're not going to have an H value, but what I want to do is give you a chance to think about how these relate to the equation, because that's the task you were asked to do, is to write an equation with this information. And what you're going to do once you have the equation, once you think you do, is you're going to type it in here so it actually graphs. Okay, so I'm going to start with just y equals cosine so you can see it pops up. And then you're going to adjust those values based on the things we just talked about and see if you can get a graph that's reasonable. Okay, when I say it's reasonable, I mean we are cycling between the two values we're supposed to cycle between, the 80 and the 120, and we're seeing that 6/7 of a second to finish the 1 beat. Okay, so I want you to pause the video and work on those pieces, the B value, the 1 over A, and the K, and go ahead and type that in for me. Okay. Going back here, our midline is literally the average of these. Right in the middle is 100, which makes our amplitude 20. Notice I'm adding the label to this as well, because our label for all of these things go with Y. Over here, going with X. Same thing with phase shift if we have it. We did not in this case. All right, but here's the tricky part. We have to figure out how to take care of the period. Okay, so I'm going to go in here and actually attach the easier parts. We decided amplitude was that, and our shift was 100. But right now, this is not doing what it's supposed to do because I'm cycling between 80 and 120, but I'm not doing it at the speed that I'm supposed to. Okay, this is taking 6 seconds-ish to complete 1 beat where we go from maximum pressure to maximum pressure again. And I need to have that happen in instead this 6/7 of a second, okay, which means this thing needs horizontally compressed. But hopefully you remember, when we see a period that does not have pi, our equation is going to have pi somehow. And you're always going to take this period and set it equal to the standard period, for us is 2 pi, times the a value. And we can solve for that. On this side, dividing by 2 pi isn't a problem, but it really would be nicer to write that as 1 divided by 2 pi. We're still seeing it in the denominator. And that way we can see this is 6/14 pi, and then we can do some reducing, 3/7 pi. That gives us a. Then from your note card, when we talk about formatting here, it starts with b, then our cosine, then our 1/a, then our x minus h, and our plus k at the end. This value in front of x is the reciprocal of a, which means we just have to flip this thing over when we put it in our equation. So our final equation should look like y equals our 20 cosine, and then this is going to be 7 pi over 3 with our x. We don't have an h value, and plus 100 for our midline. And if I fix this to actually include that, then I'm actually beating as quickly as I need to. Here's 1 second. This is just short of that, so that would be an appropriate place for 6/7 of a second, and so on. Okay. When you hit submit, it'll show you you're right. That pi does have to go on top for it to check rather than the side, although if you wrote it to the side, that would be correct as well. Okay. Now what we're going to do is one more example, but before we do that last example, what I'd like you to do is answer the question on this last one. Just want a little bit of feedback of how you like using Desmos in general, whether it's beneficial for you or if you'd prefer to avoid it, so I know how much to incorporate it into our class. When you're done with that, we're going to talk about this last little part of graphing this by hand, so we can look back at our paper and know kind of how we worked through this. And so it's going to match our graph pretty similarly, but when we're graphing by hand, we get to choose a scale to make our life easier. So we know we have to go from 80 to 120. There's no reason to start at 0 for us. We can start at 80 itself, maybe count by tens. And then we always want to label our axis, the y and the x axis, as we go through here. So we've got our blood pressure over here, and we're always going to include the physical label as well, the mmHg. On our x-axis, we have time, and that's in seconds, talking about how long it takes to complete a heartbeat. 1 full cycle from max blood pressure back to max blood pressure. And for us, that was 6/7. And when we're talking about graphing normally, so I'm going to go back to regular cosine for a second, we usually focus on these 4, it's really 5, but original points. First section, second, third, and fourth, and this distance for us is normally pi over 2. It's weird. We're not counting by ones. We never have been for when we're talking about these trig functions. So it's not necessarily wrong to count by 1, but we're only cycling for 2 periods. And 2 periods for us is less than 2 seconds. So if you are going to count by 1, you want to stretch it out. So like 1 is here and 2 is here. What I'm going to show you instead is talking about graphing using the period. We know that the end of the cycle is going to happen at 6/7 seconds, and that happens after 4 important pieces. So what I do when I'm picking a scale is I always count by boxes, 1, 2, 3, 4, and whatever that 4th box is gets to be the period. And then you can kind of work backwards to figure out what the other values are. Now here, if you take 6/7 and divide it into 4s, y'all, it's not going to come out to a super nice number. But we can say that this part is 3/7 and at least label that. So every 2 boxes is 3/7. So we've got 9/7 and then 12/7 for our period twice. From there, if we just graph looking at these features, I know I'm going to start and end at the maximum. So I'm going to start over here at 120 and end at the period. And then halfway between those 2 points, the minimum shows up. So we know our minimum already was 80. Halfway through, it's at that 3/7. And then we can visualize the middle on the midline as well. Once we have that, it's really easy to replicate what's going on the other side because we set up our scale to count by those boxes. And you don't have to do it this way. You could use way over here is 1 and way over here is 2, and you would just have to eyeball a little bit shy of that for your 6/7. Okay. Last problem we're going to talk about is an oven. Okay, what I'd like you to do is actually pause the video and try to answer any of these questions you can. I'm going to help especially on part C, just so we can talk about relationships between when we talk about a parent function in relation to some change that's happening. But pause the video and try those first for me, please. Okay. Hopefully you are okay with min and max. What I am going to have you do is remember about labels. Okay, degrees Fahrenheit was our temperature here. They have to be labeled that way. Okay, our period, you may have written it as 20 pi over 9. We're taking 2 pi times the reciprocal of this thing. Okay, so this we could really call 10/9, but if you called it just 1 over the decimal, that's great too. In general, here's how I want you to write with word problems. We're going to get that as a decimal. We don't talk about 20 pi 9 minutes. Okay, we're going to talk about it. That's really close to 7 minutes. So anytime you've got a word problem and your period involves pi, because a lot of times it won't, they'll cancel out. But anytime it does, I want you to type that in to get an approximation for me. And remember, when we're talking about cosine, we can always talk about a period as the distance between maximums or the distance between minimums. So it's saying it takes the oven. You don't have to erase anything you have, but really we're just saying it takes the oven about 7 minutes to cycle through those values. So we can say it takes the oven about 7 minutes between max temp. For us it was 431. And when it hits it again. Could have said min as well. You could have said to cycle through all of the values and back to wherever it started. Okay, lots of different ways to express that. All right, so this last one here is the one I really wanted to spend a little bit of time on, and it's talking about this original oven and comparing it to a new oven. So it says, this new oven, the manufacturer claims that less heat escapes. Okay, so let's talk for a minute about this cycling process and how it relates to periodic functions. We know that the oven's being set at a temperature of 425. But when we're putting on the oven, preheating it, the oven door is closed, and when the oven door is closed, it's trapping that heat in. And so if the heater continually pumps heat into this enclosed space, then your temperature is going to get hotter and hotter up to some maximum point. Not forever, but it will get hotter and hotter. Okay? And so at some point, that heater's got to shut off so that we don't get too high above that 425, so we're not burning whatever food that we're trying to prepare. So the way an oven works and the way any thermostat works is it's periodic because the oven's heating element is going to turn on and then shut off when it gets too hot. And then once it cools down, after time elapses, then it's going to have to turn back on to get back up to that temp that it was set at. Okay, same thing with thermostat if you're turning on the AC. Okay, you can pump it on, but it's going to get colder and colder and colder forever. Okay, not infinitely. There is a max cutoff, but trapped in there, and so at some point it shuts off until it gets warmer into an uncomfortable point and cycles back on. So, with that in mind, it says here that less heat escapes from this oven compared to the last one. Okay, and if less heat escapes, that means we're talking about changing this period here. If less heat escapes, that means it's going to take longer to get from here to here, which means we're going to have a longer period. Okay, because it's dropping temperature slower, less heat escaping. Okay? With that in mind, it says specifically the oven takes twice as long to cool from the maximum to the minimum, and that really tells us a longer period. But I want to talk about relationship between how that relates to the number in the graph. We know that this 0.9 is what's going to affect the period, but I want to talk just briefly about a plain Jane parent function. If we think about y equals cosine x instead of this transformed one, and we compare it to y equals cosine 2x, this thing right here would have a period of only pi because it cycles twice as fast. When we think about cosine of 1/2 x, our note card says 1/2 is going to horizontally stretch. That's going to make our period longer. Okay, and so it cycles slower. So a longer period also means twice the frequency in this case, because we're talking about this twice as long to cool. Or in this case, sorry, this one's twice the frequency here, direct. This one, longer period, is twice the period. Sorry about that. And this is half the frequency. Okay, because we talked about this is going to be longer, which means we're going to be going slower. Okay, it will be wider, so we have to cycle slower. So with this relationship, we have to figure out basically what the pattern is here. With this one, cycling twice as fast, or with this one, that's cycling slower. And hopefully you're seeing the relationship that relates more to this one, because we want the longer period to show up. And with the longer period, the relationship is just half of what we see in here. Again, half is the factor because of what they gave us, not necessarily the factor always. But with that, we can take our equation, the normal one, and just adjust it. Taking our 0.9 and literally dividing it in half, which gives us 425 plus 6 cosine of 0.45 minutes. Excuse me, m. Okay, the algebraic version of this, if it says twice as long to cool, it's twice the period. So that would be 40 pi over 9 equals 2 pi a. Okay, I can solve for this. Those cancel. We've got 20 over 9 equaling a, which means we would have 9 over 20 here, which is the same thing as our 0.45. Okay, up to you how you want to think through that, but get an idea of thinking back to our purple note card of horizontal stretch or horizontal compression might let you get there a little bit faster.